But I think we're ready for the keynote. So,
Thank you.
You're welcome.
Thank you, Ian. Thank you, everybody. Thank you for inviting me. It's always a pleasure for me to come to Germany. I've come quite frequently, partly because I guess I'm somewhat known here, and partly because I always find that I get great questions when I come to Germany, and that's what tells me people here knows a lot about C++. I'm not going to do that again. Okay, so the title of my keynote is about good C++ 11 coding style. And I read Len's blog, actually, and I thought that was really good. He mentioned about the fact that there are these little islands of C++. And I know that for a fact, because there's islands of computing about games programming, there's islands of computing about numerical computing, about Qt, and often these islands don't know each other. And part of C++ 11, what I think it can achieve is unifying some of these islands and building new islands as well moving forward. So let's see what we can do about that, okay? Now I have a lot of titles, but none of them really mean anything other than the fact that I tend to make a lot of trouble at the standard level for my company, for Canada, and for just about anybody who wants me to represent them. I've done things like, create user-defined literals, generalized attributes, transactional memory, just a whole group of things with regards to parallelism. So I think in a way, what I like to bring to this keynote is a certain high-level view. Let's ignore all these idealisms that I have to put in front of every slide. So the tail of this keynote is going to give you an idea of the state of the union of C++ 11, almost a year later. It's almost a year to the date when it was standardized. And then we're going to take a look at a particular topic that's come up because of what C++ 11 brings, and that's the idea of infrastructure versus application programming. And then I want to take a look at future programming models. I'm not going to actually look at any real specific C++ 11 code other than what I use as my example, because I think there are a lot of great speakers here who are going to do that. Okay. Just as a voice check, are people hearing you okay in the back? Or is there a lot of echoes? Sounds good? Thank you. Alright, so C++, I still call it 0x, C++ 0x and 1x because I've known about them for 10 years like that. I know that they're called C++ 11 and C11, but in reality, what I think about is that they tried in C++ to make it in the last century, and that's why they called it 0x. They thought that they could make it before 2010 ran out. They didn't. So to try to circumvent that, you guys have probably all heard this joke. They tried to turn x into hexadecimal, and they gave them another 6 artificial units. They didn't actually need that. They only needed b, and that would have made it to 2011. Now the C committee was a little more realistic. They knew that they were going to make it, so they said, let's call it C1x as the code name. Now that would be very clever if you think about it, the fact that they ended up being C11. What are they going to do about the next standard if it falls within this decade? We're still okay. See, we can call our next standard C++ 1x, and we're still good. I don't know what the C committee is going to do. So this is a chart that I sometimes bring to conferences, but I added a little bit with the pictures. This is a chart of C++ 11 progress, starting from 1998 all the way up to the top. It doesn't matter what's in between now. That's history. What is interesting is that this is a chart of what the people were in 1998, okay, and the people that were there in 2011 in Madrid. Specifically, I'm going to point out a few people, okay. I think we can very clearly tell Iana, he still looks kind of the same. Let me see, where is he? There it is. Right here. There are a few people there that are still on the committee that are still there. I don't have a pointer, but what about the guy with the mustache, Steve Becker? He was an editor of the C++ 11 big standard draft. I think Steve Clement is here. He's still around. And here, I believe, is Andy Koenig, as he looked back about 15 years ago. Okay. there's one guy who's going, there's Mike Miller going just going straight up. The other guy with the big beard there, he is now the chair of the core language committee. There's one guy here who was there and was also there in Madrid, and you can't see him. And why is that? Because he's running the camera. That's Tom Plum of Plum Hall Computing. So there's still a lot of guys around, but there's a lot of new guys, as you can see. What used to be a committee of about 25 people is now expanded to a committee of over 60 and sometimes 70 people. When I look at this picture, I do see myself, but nevertheless, I do see all the different people that are around here that contributed to all this. Fantastic progress. So what was the goal of C++ OS? In almost every paper you read from Beyond and from other authors, there's going to be these two, I hope. That is that it makes C++ a better language for systems programming and library building, and to make it easier to teach and learn. Whether we achieve that goal is something for you to judge, but I think we have some reasonable belief that we've done a fairly good job of that, given the popularity that I'm seeing right now. These are the rules that we follow. I have a lot more slides that talks about these rules, but I find them kind of mundane if I were to just talk about the rules and what features came out of them. So I debated a lot during this keynote whether I should go through it. I decided not to. I decided to just give these rules to you so that you can sort of take a look at them and see, and then you can see what we did. But if you wanted to see what all the C++ 11 looked like, this is what it looks like. This is the sum of all the features. Some of the underlying ones are the bigger ones. I won't go into them again. You can look at them yourself. The library also added significant improvements. It's not just a language. The library had started with the original C++ 98 library. It improved the performance by adding all-value references, context expert, and then used various templates in places to improve the compile time of the library. But they also introduced incompatibilities, which I am going to talk a little more about from the language point of view. But in the library, the biggest incompatibility is with C++ strings. They can no longer be reference counted. They have to be, and that's a nod to parallel programming. Okay? And I'm going to talk a little more about that. They added 13 of the 14 TR1 libraries. The only library they did not add was a special math library. And that ended up going to a different standard because it was so specialized. It was things like Bessel functions and Fourier transforms. They felt that, well, most people felt that that just didn't belong as part of the C++ standard. It was worthy to be its own standard. It was fantastic work. The other thing that is major about the library that was added was the threading capabilities. And these capabilities for doing smart pointers. These are enormous additions that allows you to do thread joins, how to spawn off new threads. These are capabilities. Up till now, you could only have done either under using POSIX-C or some sort of vendor package. Somehow, some different way. Standardizing makes it a lot more usable. What do we get rid of? Yes, standards do get rid of things every now and then. These are the major things they got rid of. Okay? Auto as a storage class. Can someone tell me why they had to get rid of that? It's a new keyword for auto type inferencing, right? Export semantics. It was about time to get rid of it because this was a feature that no one ever implemented in C++ 98 except one company, EDG, and they wanted to get rid of it. So it was time to get rid of it. We were happy to get rid of it. I mean, there was always a little bug out there that said, if you actually really looked at us closely, we were not compliant. And this applies to every compiler, whether you were Microsoft, Intel, IBM, Sun, no one had it. Exception specification. A little bit shocking, isn't it? The idea that you can use an exception specification to say whether what kind of object something will throw out of a function, that is gone. Okay? It was always problematic anyway because it was what was known as dynamic exception specification. What was problematic was, what if you broke the contract? What if you actually threw? These exception specifications were underspecified in terms of what would happen. So as a result, it was deemed better to just get rid of them at this point. You can still throw, of course, you can still try and catch and throw. You just couldn't specify what was exactly what was coming out. Okay? Auto pointer. This has been replaced by better, smarter pointers. Bind, bool, plus. C, by the way, also got rid of something. Get S, and that's about time, because that was always error prone. It was a safety problem. It had a lot of good things. Now, how do I migrate from C++ 1703 to C++ 11? There's actually a chapter, Appendix C, which pretty much tells you all this, but these are the highlights. The big things are things like, if you previously wrote something that was like a macro, and you try to concatenate it by placing it next to a string, well, that used to be A, B, C, D, E, F, but now it's just E, F. Because that UA in that place is now what's called potentially a prefix for raw string literal. So that new feature killed that. The other thing was something I invented called user-defined literals. And we'll talk a little bit about that because I absolutely love this feature. And I figured this is a great place to talk about it. But no, there's actually a reason why I want to talk about it. But here, what happens is that if you put it after if you put something that is a macro after the string, that is the place where user-defined literal suffix could go. And because of that, that kills that capability. Okay? Now that we have long in the standard, long's been around for 10 years plus, well, there's a slight difference in terms of the promotion sequence. Okay, you need to be aware of that. Specifically, a lot of certain integer literals that are larger and can be represented by long could change now from what used to be the topmost range, which was an unassigned integer through promotion, to now assigned long. Okay, because the availability of the new one. There's actually even more subtlety to that, because we have to try to follow C99 rules, and C99 skipped a few promotion steps for very specific reasons, and we thought it was more important to follow that. Okay. There's a little bit of rounding. I'm not going to talk about everything here. What's interesting? Narrowing. Okay, narrowing restrictions in aggregate initializers. This used to be valid in C++ 03, but because this is a double type, it is not allowed because it's a narrowing conversion. Okay. This was always a source of bug because you couldn't figure out where this would cost you nights of debugging. Because you would do this, and nobody would tell you about it, that you don't get the full value. In this case, it doesn't matter because it's 2.0. I guess I just stay in the camera range. But if you put like 2.3 or something like that, you wouldn't know. You would get 2, and you wouldn't figure out where it came from, where that 0.3 was lost. Okay. Other things. This is interesting, of course, removing the white space requirement from nested closing templates, right angle bracket, the right angle bracket feature. Now there's that something like this, which used to be valid in C++, because this is an honest to goodness redshift operating in C++, is now invalid because now this is considered closing of a template now. Because now you can't put two right angle brackets together. I think somebody's going to talk about C++ 11 features later on. Maybe they'll go over this in more detail. So that's about it. Now for my next part, I'm going to talk a little bit about one of the things that we notice about Morse. Yes, we've already seen enough to know where things are not working quite well. I love this slide because in one slide, this tells you how lambdas work. Okay? Anyone familiar with lambdas here? Good number of you guys. Anyone familiar with how they implement it underneath? Still a good number, yes. Given the fact that you guys all kind of know how lambdas work, I want to tell you how they're actually implemented underneath. You can do it now. You can probably do it now with enough macro magic to do it. All they are is that they're translated into an anonymous functor operator. That's all it is. Okay? And you can see the conversions here. If you have a captures clause, okay, which takes the values, the variables from the environment, okay, that is just transferred into the body of this class functor initializing these capture types, and in the constructor, initializing them with the actual value that was taken from the environment. Now the call itself is this tricky operator paren thing, which makes a function object looks like a function call. And in there, you pass in directly the parameters in there directly. You take a return over directly, and the statements directly. And as you can see, you can build this today yourself. Okay? That's it. That's all it is underneath. This is also called a monomorphic lambda because the parameters that you pass, you have to say what type it is. You have to say it's a student or a manager. There's a movement in the new standard asking for what's called polymorphic lambdas, meaning you don't have to say student type or manager type. You just pass in S, and whatever that happens to be, that will be taken. The way they do it is in here. They will turn that into a template. Okay, it's a very, very easy conversion to make it all work. Now, this is not exactly all the syntax for lambdas. There's a little more, and I'm going to start looking at that. With lambdas, it turns out most people were surprised by the this pointer. Okay, if you try to capture something from the environment, the this is always captured implicitly, and it's invisible. Okay, and here's how it works. To capture a member variable by reference, it's going to capture all the member variables by reference, even if you wrote capture by value. That equal sign is capture by value. I hope someone's going to talk about lambdas later on in more details if you want to know a little more about it. I'm assuming you already know the syntax, given the hands that went up. So this is how it works. If you have a lambda, and you wrote it like auto lambda equals, and the first one is the capture. And that capture takes that variable, that class, takes that class y, okay? And what it's going to say is that if you take x, x is going to be captured by value, y is going to be captured by value. Now z, this is going to be captured by value if z is a member variable, okay? And you haven't seen z, you don't know what z looks like because it's something from the environment where this class is contained. Now, what is going on here? Let me go to the next slide and you can see what's going on. Yes. Okay. Right. So here's what's going on here. We have class C, this lambda embedded inside of the class C. There's probably some class member variables just before that, I didn't show it. But instead of the previous translation, this is what it's going to look like. It's going to bring in this pointer for the class through this const pointer to C. Okay? It's going to pass it in silently as part of this constructor. And then the next thing it's going to do is, of course, I'm not going to, so implicitly these are cons, and that's why this is going to be a cons point. The operator paren function is going to be called as a const function, which effectively means that the this pointer is called as a const pointer to const C. Okay, but ignore that for a moment. This is for a later slide. What this is saying is that no matter what you do, even if you said nothing, or even if you try to say something, you're going to get the this through a pointer here. It's going to take that. It's going to take that this pointer, whether you said anything about it or not. And this turns out to be very surprising. So people have thought that this is either a bug. No, it isn't. It's actually intentional design. And because of that, people have thought, well, why is there a way we can work around that? Or is there a feature we can propose? And some people have suggested that maybe you can do it like this, so that you have to specifically say this Z in order to capture that Z variable from the Z member variable from the surrounding class. Okay? Now this is not in the standard yet, but this is what's being proposed right now for the next fix, which is in C++ 14. Okay? Do you like it? What do you guys think? So this is what's going on right now. Now let's look at the next one. This is also interesting. The idea here is that with lambda, you can't actually modify a capture local variable. And the reason goes back to the underlying implementation details that I'm going to show you. But here's the effect of it. If you have a value that's from the outside, and you capture it by value, okay, look, Mom, I want explicit copy here. I really mean copy. And you try to implement it, are you surprised that that's a compile error? How many people would be surprised by that? How many people are not? Okay. Good. Interesting. This is a good balance. By the way, this actually exactly reflects the opinion of the standard. Half the standard body was surprised and the other half was not. And when you have this kind of nearly equal division, I'll tell you the punchline right now, this didn't get accepted. Meaning that we did not want this to change. Because there's this already code out there that was counting on this. But let me go into a little more detail. Why would you be surprised? Well, you would be surprised, but just to continue my story, even if you try to capture this by value, explicitly, look, Mom, I even specified val, and by specifying here in the capture clause, I'm saying I want it to be copied. I still can't increment it. What's going on here? Because if I wrote code like this in a regular function, it's not a lambda or anything, I would be perfectly okay to increment this, and there would be nothing wrong with that. So what's going on here? To understand it, all you have to do is look under the lambda a little bit and see how it actually is formed. Now this is a much more expanded slide. It fills in all the places that a lambda can have funny things. In the middle there is this capability for you to add what's called mutable. You can also add an exception specification here too, but we won't need that for this one. Now here's what happened. In the previous slide, you'll notice that no matter what if you say nothing, by default, this operator parent is a const call. It's a const member function. Because it's a const member function, everything that comes from this body here is going to have const essentially added to it. Now, the light is beginning to go on, right? Now you see why you can't increment it. Every member variable that's being duplicated in a lambda is now const. So, no way, there's nothing you can do about modifying that. Now, why did they do that? Well, lambdas, one of the big reasons for lambda's existence is parallel programming. Every time you do this, you actually create a separate little copy of this thing. It's not the same copy. It's a separate copy, and these things have to be passed possibly through an async call, and these async calls could live and die at different times. And if there's any kind of variation or changes to these things, that's not going to work. That's why these are copies. So what do you do to make it not a copy? Well, the way you can solve this problem is there are two ways. One, you can bite the bullet and say, you know what, I'm just going to make it a reference, not a pass by value. That's okay, but if you still want to pass this to an async function, that's not going to work, because now it's a reference to the original single variable. You don't want that. You don't want a lot of lambdas all hanging on to this reference, right? What's the solution? Well, you can make it mutable. You can say this is a mutable lambda, and when you do that, all that's going to happen is that the compiler is going to put this const, get rid of this const member function here, and make it a regular non-const member function. Now you can happily change the variables as much as you like. Okay? So it helps that sometimes if you understand the implementation, you can see where this is coming from. Now, was this change, this proposed change accepted? No. The vote ended up exactly like this room here. Half the people said, I accept this, half the people said, I'm surprised by this. In order for something to pass at the standard level, we work by consensus. What that means is that we want to get almost 90%, maybe 100% agreement on something. That's how we get through something. That's how we get a feature through. It's not easy, but it does work in the long run. Okay? All right. So, a year later, where are we? This is I used this slide for my own executive management group because, and that's why, unfortunately, my compiler is kind of big up there. But, it suffices. I figured it's good enough to show you. We've been building this since 2008 in different phases of the compiler. Other compilers have too. The green guy is a GCC. They are probably the one that's pretty close, as close to finishing as you can say they are. Although the quality might be, alpha quality, but that's GCC. We kind of come to expect that in the community. Microsoft just came up through with 2012 with a lot of major features. They also just delivered the C++11 standard library now. Okay, with thread capabilities and async capability. None of the other compilers have actually delivered something like that. G++ is ready to own. The one that's coming up the rear, like a dog horse, but is now coming up and could possibly win the race is Apple's Clang LLVM. They have a lot of features coming up. They can compile Boost, maybe not Hello World, but they can compile Boost. Kind of strange. Intel, believe me, compiling Hello World is actually really hard. That's for another talk. But just think about all the pounding clues up there. It's not, those things will cause anybody problems in terms of compiling. Okay. Intel has also just issued a new compiler as well too. So this is all within this year. You can see how fast these releases are coming out. C is also coming out, so some of these compilers are also issuing a C compiler. We're talking about the C, the value and the usage of C language. My own private opinion is that C really is boxed in, okay, and it's going to be tough for them to grow. But nevertheless, mostly the open source guys have committed to supporting C11. I think very few vendors have actually, we have, but very few other, what are most other vendors saying? They're saying if you want to use C, use the C++, use the C subset that's in C++. Okay? All right. Any questions at this point? I want to switch tack here and talk a little bit about infrastructure versus application programming. This is kind of like the forward-looking motivational aspect of the keynote talk. Where we wanted to give some advice about, now that you have the C++11, what can you do with it? Now, much of this talk, I want to give credit to Beyond Structure, based on the two papers it's written early this year, and through a conference called History of Programming Language. And I only chose parts of it because I kind of wanted to motivate you to probably go read the paper. But here's what it is. Today, how is the real world using C++? And the thing is that any discussions about programming language typically focus on language features. What does the language have? How efficient are they? A more relevant question I would argue is, and this is something that Christian Nygaard, the inventor of Similar, who's pretty much Similar is kind of like the predecessor of C++, bringing in classes and things like that, have asked, and that is that if you build languages that needs a PhD to use, we basically have failed. And the point is that in an industrial context, the question that we would ask is, who uses the language? What for? Who supports it? What are the alternatives? Now, counting language isn't something that's easy to do. Counting use of language is going to be even more difficult. Do you, for instance, is a professor who uses C++ in his class considered a user of C++? Is a student working on an assignment considered a user of C++? Or maybe you want to count the number of Stack Overflow questions there are. Okay? There's so many different ways. There's no real fair distinguishing. And most of the time, I really don't get into flame wars about languages because I really don't know if they achieve anything. But here is where C++ is used today. It's obvious that it's used in a large number of places. But since most of the places is commercial, it's difficult to document. And this is one of the areas where the lack of central organization for C++ hurts the C++ community. No longer. You guys have all heard of isocpp.org? No, almost all of you? Okay. I'll talk a little bit about that if you guys want to later on. But suffice to say, we finally have our central organizing body. And this is a central body that can bring together different islands, I would propose. Okay? So this is a list of some of the real applications that's being used. As you can see, And I want to bring your attention that some of these are highly critical systems responsible for safety of a huge population. Just look at this one, Dutch surge barrier control. I mean, think of what happens if that thing failed. Okay? I mean, airline reservation systems. Think of what would happen if that failed. StarCraft. Think of what would happen if that failed. It's probably the most popular game on the planet at some point in time. Okay, we can't do Google. Well, you know, at one point we didn't have Google searches, so I love Google too, by the way. So you can see how important some of these applications domains are. So so you can pretty much conclude from this that some of the most widely used and most profitable software products ever are basically on this list. Whatever C++ theoretical. Hello? Hello? Can you guys hear me? I think I lost you. That's fine. Hello? Okay, good. So whatever C++ theoretical importance, I would say that it's pretty much fulfilled, it's pretty much met its most critical aim. And that is basically to become the most immensely useful, practical tool on the planet for programming languages. Okay. Now, the thing that I wanted to point to is that programming languages resist any kinds of useful classification. But the most important takeaway from here is that if you look at this classification of possible areas that the C++ can do, you can pretty much conclude that C++ cannot be ideal for all of those things, right? And this is something that Diana has always said right from day one, which is that, surprisingly, you might find it surprising, that a general-purpose language can, at best, be second best in a well-defined application area. And C++ is a general-purpose programming language with a bias towards systems programming. It's not focused in any particular application area, and consistently in our designer language, that is the focus we have been trying to keep in front of us. We're not trying to do it so that it accelerates database accesses. We want to do it so that it becomes a general underlying infrastructure. Okay? And ultimately, this is what it's about. Systems programming is about building infrastructures. So consider the apparent paradox here. C++ has a bias towards systems programming, but most programmers, and I'm sure most of you guys are programmers in one way or another, as I am, write applications. And millions of programmers are writing applications, and a lot of those write the applications in C++. I put to you, why don't they write them in an application programming language? For some definitions of application programming language. Many do. And the thing is that we might define that an application programming language is basically one in which we can't directly access the hardware or that provides direct and specialized support for an important application concept like database, like user interactions, GUIs, and numerical computation. So under that possibly incorrect definition, you can say that examples of that are things like Excel, SQL, even COBOL and Fortran to some extent is an application language. Okay? I haven't heard of Fortran being used to build an operating system lately or ever. Okay? To some extent, you might even say Java, C# and Perl, Python. And for good or bad, C++ is used as a general-purpose programming language in a lot of these areas where a more specialized language would be better suited. Wouldn't you say? Why? The thing is that C++ does have a niche, and it is a large niche. Okay? Here, application programming languages basically gain their advantage through some kind of specialization. They might have added conveniences,
or through eliminating some difficult to use or potentially dangerous features. Often there might even be a runtime or a spatial cost to this facility. So simplifications are basically based on some sort of strong assumptions about the environment. So if you happen to need something fundamental that was deemed unnecessary in the design of this particular application language, or don't need the added convenience, then C++ becomes a viable candidate for that. The basic conjecture in which C++ is built is that with a lot of applications that have components for which that's the case, most of us do unusual things at least some of the time. And when you do that, the positive way of stating this is that general mechanisms being specialized, special purpose features for the majority of applications that don't completely fit into a particular classification. Or they might have to collaborate with other applications, or they might significantly evolve from the original narrow design. And that is where C++ comes in. So I think what we can say is that the impact of C++ is that the main contribution was and is through the many different systems that are being built. I can switch that to that too. Hello? Hello? Wow. Tremendous improvement. So I would say that the primary purpose of a programming language is to help build good systems. And C++ has become an essential ingredient in the infrastructures on which our civilization is built. This includes things like telecommunications, systems, personal computers. Pretty much everything under the sky, there's some C++ in it. And and it's also been part of some of the most inspiring moments in our time period. Similar, for example, the Mars rover and the sequencing of the human genome. Okay? So what am I trying to get at here? I want to point out to the fact that our lives are directly affected by software correctness and efficiency. Focus on those. Software correctness and efficiency. Basically what I'm saying is that this implication puts a whole new emphasis on the old challenge to software developers. And that is to deliver code that is both correct and efficient. Okay? The point here is that if any of these systems fail, people are injured, or lives are ruined, or economies become ruined. And that has a major impact in society. Look at the flash crash a couple of years ago. That has amazing impact that's still rippling through society right now. And the point is that you might not even be able to fix it. In some cases, it's impossible to fix a space probe. In other cases, it's just economically unworthy to fix a cell phone problem. Okay? You might as well just throw a whole cell phone away and completely replace it. What I'm directing us to do is we need to find a better way to deliver code that is both correct and efficient. And the benefit is far-reaching. Correct and efficient code could mean your cell phone battery may double its lifetime. The reason my cell phone is dying all the time after 3 or 4 hours is because somebody put a bug in there and is constantly sending out ping requests for no reason. I have no idea why it's doing that. I'm still trying to track down the software that's causing that to happen. Because it didn't happen before I downloaded the latest upgrade. Okay? It doesn't mean fewer server farms. Even reductions by one of server farms have huge implications in terms of the energy that's used. Okay? And it might mean fewer people are hurt. The cost of failure, and I call software where failure can cause serious injury or serious economic disruption, infrastructure software. These software have to be dependable and meet far more stringent reliability standards than regular software. Engineers have had this for years, but not in software. Okay? Because ordinary personal computers and smartphones are useful platforms for applications also serve as infrastructures in any operational use of that word. And the fundamental software in each platform is itself an infrastructure. And one of my inspirations here about this is that if you look at the AT&T telephone switch network, it had no more than 2 hours of downtime in 40 years. Even having a truck crash into the building is not an excuse for that software to fail. Okay? Our civilization basically runs on software. You would starve without it. Software is being used to plan all the routing of how food is being distributed and moved. Our dependency is increasing, there's no question, and yet the complexity is increasing, and the hardware requirement is increasing, but our comprehension is not. It is limited, okay? Unless we have some sort of different kind of human being. So a lot of improvements in system reliability over the years have been achieved basically through deep layering of software. How do we do that? What happens is that each layer distrusts the other layers of software in the system. They check and recheck information. And then furthermore, the layers of software used to monitor hardware. And if possible, compensate for those errors. A lot of cases, these applications are interpreted or run in a virtual machine that intentionally isolate them from the hardware. And these efforts and these other systems that are more reliable, but they're huge and they're not well understood. The other contribution to improving reliability is called massive testing. For us to put a compiler out, we have something like 60,000 lines of code tested through every single option. And it takes us almost a whole week to get through that test. Okay? And this is one cycle. The cost of maintaining and deploying software is basically increasing. And software is going to continue. We know that human expectation grows even faster than software performance. So ultimately, further consumers of computing power are things like tools and languages that try to make programming easier and less error prone. What they do is ultimately move decisions from design time to run time to catch the error. And this is the point of this part of the keynote, is saying what C++ 11 brings to the table is that it's more upfront compile time checking and more semantic-rich information that can allow you to figure out when something is going to go wrong before they do. We basically compensate for, at this point, I claim that we basically compensate for a lack of understanding by increasing our requirements for computing power. So here's C++ 11's place. You've been waiting for this. Why is he going off on this tangent? If it's a tangent. The reliability and energy efficiency requires a lot of improvements in a lot of different areas. And here I discuss the implications for software. And here, not necessarily my conjecture, this is actually the honest conjecture, and I fully agree with that, is that we have to structure our systems to be more comprehensible. Because for reliability and efficiency, we have to compute less to get the results we need. Doing more with less is an attractive proposition, but it does cost. Okay? It costs in that you have to do more work up front with a better language that is capable of doing that. Okay? And this is what I hope will be delivered in the next 10 years. Right now, I believe that C++ 11 most closely approximates that ideal because of what it has. But I certainly hope that we can see better languages and tools over the next decade for that. So what's it mean to compute less? Some anecdotal stories. Now, I fly Air Canada whenever I travel. In fact, when Yen asked me to come over and give a talk, I said, well, I'm from Canada and we usually fly Air Canada. Now, there is one interesting incident that happened about 20 years ago, and some of you might have known that as the Gimli glider. It ran out of fuel at 12,500 meters halfway on its flight across Canada. Now, miraculously, no one died. It actually glided to a safe landing in Gimli, Manitoba, which is why it's called a Gimli glider. And some of you have, and immediately people have asked, how can an airliner run out of fuel in mid-flight? You can see where I'm going with this. The next example is in 1999, September 23rd. The Mars climate orbiter, costing something like $654 million was lost due to a navigation error. Both of these cases, the real problem was because there was a problem in terms of the computation between metric and imperial units. Some of the software was kept in imperial units, and some was kept in a metric unit. And you might ask yourself, how can this be? Some of the experts who are programming this are experts in their own field. And all of us are taught about conversion right from high school. My son is learning, he's 6 years old, he's learning how to do conversions. How can people forget this? Well, let me just expand on that a little bit. But look, focusing on all this, you can see that specifically with the Mars orbiter, what we have here is the loss of something like a lifetime work of 200 very good engineers. We lost the scientific mission results until we can actually replace it. The consequence of this is enormous. So, why is it that programming languages and no mainstream programming language support Unix programming? And yet, every general purpose language is going to allow a programmer to encode some value as a pair of quantity and a magnitude and a unit pair. And the answer is that it just wasn't worth the time, oddly enough, for language designers, battling all the different requests and things like that, to add in the ability to support unit programming natively to a general purpose language. When you do that, you double the size of your data, you have to check the computation at every stage, and space probes and cell phones are notorious for not having enough memory and having compute bound limits in terms of the time it takes to do things. So engineers just figured we're going to try to keep track of this in our heads or in the documentations. And the problem is computers don't read documentation. In fact, I suspect most of you guys don't read documentations. Okay? So here in this case, they lost. They just plain lost the battle. Compilers, they don't read docs, and they don't read minds. And what happens is that a number crossed an database without the unit. It took on a totally new meaning. In fact, it actually changed by some value or multiple of something like 4.5. And the result is the orbiter landed something like 250 miles away in a different place at a different altitude than what it thought, and therefore just basically crashed at that point. And that's what happens. So the question is, why would general purpose language support Unix? It can, because it's hard to check it at compile time. And some of the other issues are probably historical, but ultimately, what we want to do is it possible for a tool or specialized language to supply SI units? Yes, it is. But specialized language, as I said before, suffer from high development and maintenance costs, and tend not to work well with other specialized tools and languages. The features work best when they're integrated into a general purpose language and don't need a separate tool chain. Interestingly enough, C++ 11 is showing that a sufficiently expressive language can achieve compile time unit checking without any kind of language extensions. And I'm specifically talking about user-defined literals. Yes, finally you get to see some code. If you aren't familiar with modern C++, this might be a little bit cryptic, but it's fundamentally simple. Okay? In C++ 9803, you could create unit programming by encoding as, first of all, the unit as an enum. And then you can create a template type on that enum, from which you can now create different instantiations based on the position to be meters, kilometers, second, okay, or kilograms, sorry, to be able to, oh no, that is kilometers. Kilograms, yeah, it says so right there. And you can tell immediately what kind of unit it is. And in fact, something like this has been written 10 years ago. Fermilab was a really good example of this kind of library. Yet, did people at Fermilab use this? No, none of them used it. Yes. Did you use it? Okay, one guy. Because it was important. I know that the job that is an important application area. But for most people, they don't. Because scientists just don't want to write code like this. With user-defined literals in C++ 11, you can write something like this. You can create a user-defined literal using this operator, double quote. This space is absolutely necessary. And then you can create these second square or second. Now, By the way, you can't do this. If you do it, you actually have to add an underscore in here, okay? But that's just because the standard need requires you to do that. But that's how you can do it, and the result is elegant. It's clear, and it's simple to see that something like that is either a second, or kilogram, or even second squared for acceleration. What we're saying here is that we want something that is type-rich programming at compile time. User-defined liberal in this case is not just syntactic sugar. The notation matters. SI units are important and should be supported. Essentially, there's a variety of other notions. But which one? The fundamental point here is that we can improve code quality basically without adding runtime cost. The use of a static type system, and this is my point finally, improves code quality by reducing the number of errors and moves checking to compile time back out of the runtime. In fact, we can move most of the simple computations to compile time, as you know, using C++ template and meta-template mechanisms. Compile time computations have been done for years in different ways. People do it by using pre-computed magic numbers that they would add to the input. They would do it with a bunch of messy and error-prone C macro. Or they might, but for infrastructure code, I argue that that is just not good enough. You need something that is fundamentally supported as an integral part of the language. And my point here is that ultimately, the compile time evaluation and immutability in general becomes more important as more systems become concurrent. You just simply cannot have a data race on a constant, as you can see. Okay? So, when I first write code, I had to squeeze out, pretty much every last bit out of a processor. And a good rule of thumb was that I had to use some rule of thumb ultimately to know how much to put in. In today's world, what we have is, what I would do is that I would basically organize my code and data to minimize memory usage or cache misses and so on. So my first order of rule is try to do things that don't store data unnecessarily. I want to keep data compact and ultimately access memory in some sort of predictable manner, being aware of how cache and cache locality and fault sharing can happen. So in practicing type-rich programming, I want to address the issue of correctness and what it requires and what it requires in terms of making progress in what areas. So the two areas that I think of is that you have to eliminate basically what can be caught by a good production compiler. And what I'm claiming is that catching design error, which is the better goal, is ultimately possible if semantic information is encoded in the type system. I say that again. You want to encode semantic information in the type system. For example, here what we have is a very simple example of increasing to some speed, a double of the speed. Now this is an error that's waiting to happen. Maybe we understand the requirement for an argument, but they only appear basically in comment or documentations. So we don't know whether increase to, is increase to 7.2 correct? Does 7.2, is that a speed? What unit is it if it is a speed? A better try here would be the next line, which is increase to speed s. Now this is fundamental knowledge that most of you guys probably know already, so why is he repeating that? The point is that given a reasonable definition of speed, then something like increasing to 7.2 is an error, and increasing to 32 meters per second is probably okay. That's where this comes in. The point here that is important here to know is that parameters should not be near universal type. This is not just an issue of units. I have basically a philosophical problem with parameters like that. For example, an integer can represent just about anything. Here, I have a rectangle of integer x, y, h, and w, and I pass in this 100, 200, 50, 100. What does that mean? Is h and w the coordinates of the bottom right corner of the screen? Or is it a height and width, like what the letter seems to imply to me? To avoid error, we have to be more specific about the rectangle's requirements on this argument. We have to say something like rectangle point xy with an area hp, and in that case, I can say rectangle point 100, 200, and with this area argument is less error prone. I can also give another version for the other use case I'm interested in. Something like rectangle or point top left and point bottom right. The point here is that the simple user-defined type should not impose overheads compared to built-in types. Okay? Finally, there are a lot more to this, but I want to motivate you to understand that the guideline here is what we're saying is that you have to keep things simple. You have to leave more time for, this basically is good sense, because it leaves more time for complex things. And generalizing all the cases to the most complex is ultimately wasteful. But more important, the point that I want to make is that society, infrastructure software requires a much more stringent correctness, efficiency, and reliability. These three terms are tied together. Correctness, efficiency, and reliability. Otherwise, people in society suffers catastrophically. These things need upfront design, static structure with enforced type systems, compact data structures, simplified code structures, and better tool support. And I would ultimately argue, for some of you guys who are professors in academia, that education for infrastructure developer should differ from that of application developers. And ultimately, that's one of the best ways we can serve the future. Now, Neil Bohr have always said that it's hard to make predictions, especially about the future. And in a way, I'm trying to make predictions here, and maybe that's the ultimate point of what I'm trying to do. I believe strongly that these things are related. These three terms are related. And the trend in hardware and architecture is going to increase its effect over the next few years. And heavy use of software layer will just add to the problem. So now I'm going to move us away towards the future programming model, which is what I alluded to in the last point. So what do we do now? The new C++ 11 standard is 1,353 pages. It's double the size of C++ 03. The new C11 standard is a little bit bigger. OpenMP 3.1 is 350 pages and growing. We're going to release 4.0 in about 3 days. Is it good enough? No. After seeing all this, it's becoming clear what is missing in C and C++ and OpenMP. And both languages are racing to address those issues. The question here is about beauty and elegance. Nearly every new C and C++ feature makes for beautiful and elegant code for developers. Now, I love C++. You guys probably know that. But here I am. I'm not doing something here to denounce what C++ is. I'm raising a warning flag, and this is a warning flag that many other industry technical leaders have also raised. SPL, of course, is renowned for its elegance. And I'm sure you can sort of figure out what beautiful code looks like. Just stare at that and sort of insert your own vision of beautiful code there. And the question, of course, is elegance, people have said, is efficiency, or is it? Or only lacking beauty we gain in efficiency, or does it? So here's a bit of beautiful code, C++ 98 and C++ 11. On the left is how you would walk through a vector and check for some value. On the right, using the beautiful new lambda syntax, you would do the same. Much more compact, much smaller, a few characters less. But what's wrong here? And this is something that was pointed to during multiple different talks, first by Sean, but Sean Parrott at C++ now, but he got this from Russell Williams, okay, who looked at this and thought, does your language allow you to access all the data blocks on your machine? I think the answer is pretty obvious now that it's not. It's not the case. And the question is, with apology to Jordan by George Herbert, is there in truth no beauty here? So if I ask you, does your language allow you to access all the data blocks on your machine? You might say, what a quaint idea. That was never possible. Not totally true. That was possible about 11 years ago. It's not possible because in the last recollected memory of 10, 11 years, that has become impossible. People come up with answers like, gee, I thought it was natural to drop out into OpenCL, CUDA, or some other language in order to get access to my GPU. Or you might say, why? I just use my language like a cool driver. It's a great scripting language too. But for real kernel computation, I use Fortran. You would be surprised how many people use C++ as a driver mechanism to get a Fortran code for the actual computation. Other people might say, I like vectorized code, so my vendor offers me intrinsics, built-ins, and they will tell me they can auto-vectorize. But I'm not really sure how much they can really do, so I'm looking into OpenCL right now. Another thing is that somebody might say, I used to use one thread, but now I have multiple threads, multiple cores, and I can get that now with, thank you, C++ 11, or with OpenMP, or thread building block, or Silk, or some sort of continuation pattern. Another guy might say, I know I have a transactional memory core somewhere, so my vendor offers me built-ins to access those, to create my own transactions and wrap it around my kernel code. Last guy might say, gee, I never used any multi-threaded code, I just use single thread. So that C++ 9803 was all I needed. Okay, so what's the reality here? The question here is, of course, is it true that there is a language that allows you to access all the GPUs in your, all the data blocks, all the vectorized units, all the transactional memory units in your machine? And it's obviously a rhetorical question, isn't it? There isn't, not yet. Every time you want to do something more efficient in the last decade, you usually have to drop out of this base language. But let's go back and take a look at the power of computing. In 1998, when C++ 98 was released, Intel Pentium 2 had 0.45 gigaflops. There was no CD unit. SSD came in the Pentium 3 a year later. There were no graphics cards, GPUs. GPUs came out a year later. In 2011, when C++ 11 was released, Intel cores i7, I just bought one, it's got 80 gigaflops. It's got a SIMD unit called AVX, and it's not even AVX2. And through this interesting calculation, you can tell that it's got 140 gigaflops. I just bought an NVIDIA GTX 670 graphics card, about $450 US. I don't know how much it is here, and it's capable of 2,500 gigaflops. How did I program this? In 1998, a typical machine had this amount of flops, and I use an example basically of how long that arrow is of the flops. Single-threaded C++ and C99 dominated this picture. It was perfect for this sort of thing. In 2011, a typical machine had the following flops. You had 2,500 gigaflops on the GPU, and to program that, you have to use CUDA, OpenCL, GF, or C++M, Intrinsic, OpenMP 4.0, which is coming. If you want to program the vector unit, you have to use, again, Intrinsics, OpenCL, or maybe your compiler is capable of auto-vectorizing it. And that's, I try to use a reasonable comparison of the two, but I probably didn't quite achieve it, but you get the idea. To program a CPU, if you use multi-threaded, it's probably this much. And it's about 80 gigaflops on 4 cores. And you can now use C++ 11 for that. You can use OpenMP or TBB or Silk. Under this kind of domain, how important is R-value reference? How much performance does it buy you? And again, I qualified that with saying I do love C++. And yet, I'm telling you, I'm probably being generous with this arrow. It's probably a dot in terms of the performance that it's giving you, considering how much you need to do to get access to the other machines. Going back to this, you can see how different this picture is between the two. This is very similar to the keynote that Sean Aaron actually gave at C++ Now to some extent. But I'm extending this analogy too, because I also want to look at the fact that I'm living in a world where I can see some of the things that are coming. What happens if you have transactional memory? IBM Z machines, 390 systems series machines, have transactional memory. Blue Gene Q has happened for a long time, but they were not using commodity stuff. Intel has, well, the next Ivy Bridge is definitely going to have, the next laptop you buy will probably have transactional memory on it. And how will you program that? What if we add FPGA to it, so that you can actually, you can feel programming on this capability. Maybe in future you can write C code with some sort of OpenMP, so that ultimately what comes out is Verilog and DPR and an FPA image. But that's not happening yet today. What about in high-performance computing? This is an area Sean and I agree with. He lives in the commodity market. Being IBM, lives in 200,000 core market of high-performance computing. I'm going to supercomputing right after this talk. But In that world, we're talking about exascale computing by 2018. Okay? And there's problems with that, like what's the energy bill and all that. But ignoring that aside for a moment, that revolution started with the IBM Roadrunner, where we introduced the first petaflop machine. Next year, Cray will probably come out with something called Titan, using commodity. Yes, we can using commodity components to get you to 20 petaflops. And the commodity component they're talking about is very much like the Roadrunner configuration. It's basically a CPU core with thousands of GPU cores. Both of these use accelerators, which is a large amount of ALU, a lot of fast local memory, and minimal control logic. Stopping to take a look at parallelism, we know that there are different kinds of parallelism. Functional parallelism, what we do now, and data parallelism, how we program vectors. And the two are mixing, and a lot of it is transferring to the GPU. So the question here is going to be, what does the new C++ standard that's coming up now will serve in that area? Well, right now we have a lot of study groups, in fact 11 of them. There's databases, feature tests, ranges, concepts, reflections, concurrency, modules,
File systems.
File systems, thank you, networking, transactional memory, which is what I share, and numerics. In the concurrency group, I'm going to skip this slide for time purposes, but I want to get to a few of them here. Under parallel library algorithm, there's several proposals to make parallelism easier to use by providing algorithms directly to support the C++ standard library. The next C++ standard library will be parallel. And some of these could support GPU, namely NVIDIA's Thrust and the possibly Microsoft PPL. Google also has a bunch of proposals. We also have proposals on asynchronous operations, and these are generally unstructured parallelism. We also have fine-grained parallelism. This is where the Silk proposal comes in, through strict fault-drawing parallelism and vector loops and parallel loops. Okay? I'm going to stop here. There's a little more to talk about, but I think this gives you a sort of flavor of where it's at. I'm going to jump right to the conclusion here. In terms, I was going to talk a little bit about GPUs from OpenMP, the new TR of accelerators and transactional memory statements that we have for the new proposal. But what I want to do is I'm just going to try to close this keynote here to point out that ultimately it's a heterogeneous world. CPU is great for serial tasks, but discrete GPUs these days can excel a data parallel problem. I don't know if GPU is a flash in the pan. I do know that data parallelism isn't going away. You can also have what the people call fusion GPUs, which live directly on chip, sharing memory with the CPU. We could have transactional memory using something like this, or something like an FPGA core. The question is, which parts do you approach your runner on which device? Where do you keep your data? When do you communicate synchronized between CPU and GPU? And the question for you as an audience is how to write code that can survive all this. Okay? I'm going to close with some discussion about future programming styles. We are interested in more focus on functional programming through lambdas, rather than imperative programming styles. We know that shared references to objects breaks down in massive parallel environments. We want to use less inheritance because it encourages ownership. We want to move away from reference semantics to copy semantics. The key idea is that in value semantics, using C++ R-value references and loop constructor, you can actually achieve some pretty amazing things, which I think another speaker is going to talk about. Okay? If we don't have factorization, GPGPUs, or scalable parallelism, TM and FPGA, then C and C++ over the next 10 years could just relegate into just some scripting language, driving you to get out of that, to get access to the other 99% of the machine. And I claim that would be a tragic loss. Ultimately, what we want are being able to run directly STL algorithms directly on accelerators, TM, or FPGA. That is the goal that I see for the future. Thank you very much. I apologize, I'm over time.
Well, thank you, Michael. That was very nice.
Okay.
Are there any questions? Name call.
Since you're from the standard committee, maybe you can give some insight on specifics of Lambdas. First of all, why did you decide to treat the this special so that the members are captured by reference? That's one question. The other one is why didn't you allow Lambdas to be assignable? I mean, they're copy constructible, they're move constructible, they're unassignable. What was the reason for that decision?
They mostly having to do with concurrency, and to be honest, I probably am not going to be able to remember exactly why. We did try to treat move constructible a little bit in this last go around at the Portland meeting. There was a paper to try to treat that. The reason this was captured by implicitly was deliberate design. And unfortunately, I still can't find what that deliberate design is. I promise you, I'm going to try to look it up. I've been trying to find it ever since this discussion brought up. And I'm like you, I'm still wondering why that was implicitly there. Okay? So unfortunately, I can't answer that question. Sorry.
You make the case for having a rich semantic encoded into Spark system, which I think that is the way to go for doing anything meaningful.
Thank you.
My question is, shouldn't the languages allow us to do a proper compile time introspection too, so we can actually try to get more structured information from the semantic and compile time, and how does the compiler should be adapted so that the Sentinel compile time problem with C++ to be eliminated?
Okay, so you're asking, is it possible to do better compile time reflections? And absolutely. That is exactly what is going on. The other major part of the standard that's going on right now, where they have a lot of compile time reflection proposals being put forward. Now, you're already familiar with runtime reflections. You have RTTI, which tells you what the type is, but at runtime. It turns out that with not a great deal of compile time cost, it is possible to do better compile time reflection, giving you information at compile. You can already do that today to some extent with trace classes and things like that. In C++ 17, I'm almost certain that some sort of reflection capability will be there. That's why there's in fact a study group to support that. Whether that can be implemented efficiently in compiler, I think was your second question, that I still don't know yet.
Okay. Yeah, I think we have time for one more question.
One of the most important features of C++ OX was concepts, and this got cancelled in 2009.
Right.
Which was a big disappointment for a lot of people, and I'm very interested what the plans are and the developments in the fields of concept and what we can expect for the future.
Concepts will, thank you very much for that question, by the way. I know that would come up. Concept was cancelled in 2009 in Frankfurt through what they call the Frankfurt Accord. Sounds almost like a spy novel to some extent. It was deemed that it caused too many surprises. In fact, what it did was it meant that at the standard library level, to use concept, even writing a simple print function, you had to generate a concept map. That was just too hard to teach and learn for most people. Will it come back? Yes. Concepts almost certainly will come. In fact, there's a concept on implementation on client. There's a study group started on concepts. The thing that I'm betting my money on is right now, concept will probably come back as what's called concept light, meaning that some form of the parameter prototype, a template parameter prototyping will probably come back. That is motivated by the fact that there's a competing proposal right now called static if, which is going in, which is potentially competing with concept, and that's what Beyond is trying to make sure that the two of them don't both go in. One of them will go in. And if one of them will go in, my bet is concept light. I personally prefer concept light, which if you strip away some of the representational aspects of creating maps, of the concept map, most of it is really talking about the ability to do template parameter prototyping. Any other questions? Last questions? We can also talk more during the break.
I think due to the time we have to cancel the questions now, and you can ask my